we're in chapter 4, and what we want to do is look at a confidence interval on a single mean. Now, so for confidence interval on a single mean, it works just like the proportion did. In other words, we're going to, from our sample, we compute or calculate the observed mean our average, and we call that observed mean x bar. And the sample, so observed mean, sample standard deviation. S. All right, so we have some data. It's numerical data. We can take its average and we can find its standard deviation. And so we do that, and then we're going to make an estimate based on a hypothesized distribution. And so that estimate, we're going to center it at x bar. So that's the best point estimate we have is x bar, the sample mean. And then we'll build our interval by taking plus or minus. Now here, I'm going to write a t, and typically, let's see, t of, and I will write n minus 1 here and put alpha over 2, and then times the standard error. Now again, with the proportion, what we did, so for a proportion, we used p hat. Well, that's basically an average again, right? Number of successes over number of trials. So that was just an average. So that's just like the x bar, plus or minus. And then we pretty much just wanted the 95% confidence interval. And so we always just used 1.96 or 2 if you're being just approximate, times that standard error that we had to compute. So it's the same idea. It is exactly that same idea. The 1.96 just had to do with, again, the normal distribution. And if I went out this way, 1.96 standard deviations, and went out this way to negative 1.96 standard deviations, then the amount of population, or the total area under that curve mathematically, is 0.95. And if I wanted a smaller interval, I would have to drop my confidence. If I wanted a larger interval, I could increase my confidence. But typically we go with the 0.95 because that goes with our alpha of 0.05. Now, so a way to write 1.96 would be z 0.05 over 2. There's the alpha that this was based on, and over 2. And why over 2? Well, because We don't want this and we don't want that. So total, that has to be our 5%, so it's 2.5% on each side. 2.5% there, 2.5% there. That's why they talk about the 0.05 over 2. But that's all the 196 is. I could use that, and your textbook did, I can use that notation. So what's different here? Well, it's this t now, and it's now t alpha over 2, and typically we're going to use 0.05, so it would be a lot like that 1.96. So t alpha over 2 of n minus 1 is a t distribution instead of a normal distribution or a z distribution, right? They use z here. A t distribution with n minus 1 degrees of freedom. Now, mostly this matters. It matters a lot, actually. It matters a lot for small sample sizes. Now, what's a small sample size? Generally, in most textbooks and so forth, they would say n less than 30. Some might say 25, some might go up to 35, but, somewhere around 30. Okay, so if I have fewer than 30 observations, using the t distribution instead of the normal distribution is pretty important. Now, why? What's the difference? Okay, well, the difference is that if I start with a normal distribution that looks kind of like that, so this is normal, then a given t distribution, depending on the degrees of freedom, will be shorter and wider. Okay, so here's a t. That's a t distribution. It is shorter and wider. And the reason for that is what's really going on is we're still assuming a normal distribution. But with small samples, there's a lot more variation in the sample means. Okay, so that's the deal. And in your textbook, now I'm not going to show it here, but in your textbook, you have a table at the very end, and it is a table of the t distribution. And what I'd like to do is just sort of compare that t alpha over 2 idea. And so when one looks at that table, so we have degrees of freedom, okay, and this is just your sample size size minus 1. And then it has your a t of 0.05 over 2 of the degrees of freedom. So that's where you get the n minus 1 part that we did. Okay, so sample size minus 1, or n minus 1. And so it starts with 1. And remember that for us with z, this z 0.05 over 2 is the number 1.96. Okay, well, it's really big if I have a sample size of 2. So this is sample size minus 1 is 1, so that was 2. This number, all of a sudden, to get 95% of your data, you need to go out 12.7 standard deviations instead of about 2. Big difference, right? If I go up to a sample size of 3, so my degrees of freedom are 2, then it does drop down quickly to a 4.03 or 4.30. 3 gets me to 3.18. Degrees of freedom of 4 gets me to a 2.78. 5 gets me to a 2.57. So you see, even here at a sample size of 6, because degrees of freedom of 5, I'm still quite a bit bigger than 2. I mean, it's 2.5. And so, we're at 5. Now, if you keep going, what happens is by the time we get to a sample size of 29, which would be degrees of freedom of 28, we're getting down there. We're down to a 2.05. And so when we hit a sample size of 30, the 29, actually, that's still 2.05. So it's definitely still bigger than 1.96, but, on the whole, if somebody were to say approximately, what is it? Oh, that's about 2, and these are about 2. So that's why a sample size of 30 tends to be the cutoff for a small sample. So, we need to use that table to get these t-values. Okay, and so if I have a set of data with a sample mean of x bar equal, we'll go with 5, and sample standard deviation, so standard deviation, S equals, say 2, and N equals 6, then our 95% confidence interval is, well, okay, so what do you got to be careful here, because it's saying standard deviation is 2, right? S equals 2, and so you need to actually, maybe I'm going to change N just to make my life easier. Okay, so let's make N equal to 9. Okay, so we'll do that. We'll make N equal to 9. And why did I do that? Because I want an easy square root to deal with. Okay. And so with that, I would need to do my x bar, right? So 5 plus or minus. Now I have to go look up t. Well, so let me write that as x bar t of 0.05 over 2 of 8. Okay, and that's all one number. That's just a long name for a single number. And then times the standard error. Okay, but that is x bar plus or minus t 0.05 over 2 of 8 degrees of freedom. And the standard error is my s over the square root of n. Okay, so to get that standard error of the mean, I need to do that. And so now I can kind of fill things in. Now I go back here and I look for 8 degrees of freedom. Oh, bummer, it's not there, but it is. I can fill it in now. 8 degrees of freedom is 2.31 is the value there. And so this is 5 plus or minus 2.31 times, what was that, 2 over the square root of 9, or 3. So this is 5 plus or minus 2.31 times 2 over 3. And so that's going to be 5 plus or minus, okay, well, that's 4.61 divided by 3, which is a little more than 1.5. So this is 5 plus or minus 1.537. Okay, and so there is my confidence interval. Now I can write it down with the 5 minus 1.537 and 5 plus 1.537, and so I get what, 3.463 up to 6.537, and there is my 95% confidence interval. Okay, so what did I need in order to do it? If you give me some data, even if you just give me a line of data, well, I need to calculate the sample mean. I need to get the sample standard deviation. I need to count how many items are there. And then I need to be able to look up this t 0.05 over 2 of the n minus 1. And so if I have those, then I simply, place them into the formula and get my standard error, get my multiplier based on the distribution I'm using, and I get my confidence interval. Now, there's, I said this is for small samples. We use the t-distribution, and that was anything under 30. Well, what happens if you have 50? Is it still okay to use the t-distribution? Absolutely. Because what happens is if you go to t of infinity, okay, so in other words, you have a lot of data. That this is the same as the normal distribution or the z distribution, okay? And if you look down at the bottom of the table in our text, it's at 500 actually. T 0.05 over 2 of 500 is equal to 1.96. And it never goes below that because of the way the t-distribution is made. It's based on the normal distribution, and it's just asking about sample size. So when you get up to 500, there is absolutely no difference in the numbers between the t-distribution and the normal distribution. Okay, so in that way, you know, and so even if you had 1,000, you could still use a t-distribution. Does not matter. Okay, but this is a confidence interval based on that t-distribution, and in this section, you know, that's just the safe way to go, is just use a t-distribution to get your multiplier for your standard errors, right? So how many standard errors? Well, instead of about 2, we needed about 2.31. Okay, and there we go. That is a confidence interval on a mean.